Module 2, Lecture A, DataFrames and Schema. By the end of this lecture, you will be able to create Polars DataFrames and LazyFrames from in-memory data and external files that are commonly used with pandas. Inspect and adjust Polar schemas to ensure column names and data types match expectations from existing pandas workflows. And compare pandas and Polars data loading patterns to identify where direct one-to-one translations are possible. Building Polars DataFrames, dictionaries, and lists. A simple way to create a Polars data frame is to start from Python dictionaries and lists stored in memory. You can use a dictionary where each key is a column name and each value is a list of entries for that column. Polars then interprets each key as a column and each list as the column's data, forming a table you can work with. This approach is especially handy for quickly prototyping or organizing small datasets before saving them to a file or database. Lists are important because they let you work with data both by rows and by columns. In real datasets, information often comes as sequences of records, such as customer entries or sensor readings, where each record is a dictionary or a tuple. Polars can turn these nested records into a data frame by aligning their fields into columns, which is especially useful for JSON data from web APIs or combined outputs from several functions. By understanding how Polars handles lists and dictionaries, you can convert semi-structured data directly into an analysis-ready format without creating intermediate files. Using dictionaries and lists is a practical way to move from small, in-memory data to larger, more formal workflows with files or databases. You can begin by experimenting with a few records, such as website traffic or financial transactions, and load them into a tool like Polars to explore and refine your data structure. Once you are satisfied with the column names and value types, you can apply the same structure to larger datasets stored in standard formats. This approach creates a smooth bridge from informal data exploration to more systematic and scalable data analysis as your project grows. Python code, dictionaries, and lists. This section focuses on creating Polars data frames from basic Python data structures, such as dictionaries and lists. It explains how column names are automatically taken from dictionary keys and from the fields of list records. You will see how these different inputs produce slightly different data frame structures. By printing small data frames, you can directly compare their layouts and better understand how Polars interprets and organizes your data. The line with the exclamation mark and the pip install command is a shell command used to install the Polars library, which is needed to create and work with data frames in the script. The exclamation mark shows that this command is intended to be run from within a Jupyter notebook or a similar environment where you can execute shell commands directly. The quiet option tells pip not to display the usual detailed installation messages, keeping the notebook output cleaner and less cluttered. We begin by importing the Polars library, which lets us create and work with data frames in Python. Polars is designed for efficient handling of large datasets and offers functionality similar to pandas, but with a strong focus on performance and speed. By importing it, we can build, manage, and analyze structured data effectively within our Python environment. We begin by creating a dictionary where each key is a column name for our data. One key, called product, is linked to a list with the items book and pen. And another key, called quantity, is linked to a list with the numbers 3 and 10. This setup lets us directly map each key to a column when we build a data frame. As a result, our sales data is organized in a clear, column-based structure that is easy to work with. Using the Polars library, we can create a data frame by passing in a dictionary where the keys become the column names, and the values provide the data for each column. This method offers a simple way to turn structured data into a data frame. Once in this format, the data is easier to manipulate, explore, and analyze. Printing the data frame created from a dictionary lets you quickly check that it was built correctly. By looking at the output, you can confirm that each dictionary key has become a column name and that each list of values appears as the data in that column. This visual check helps ensure the structure and content of the data frame match what you intended. We create a list where each item is a dictionary representing one sales record with two fields, product and quantity. For example, one record might be a book with quantity 3 and another a pen with quantity 10. Using dictionaries with the same field names for each record makes it easy to later convert this list into a data frame, where each dictionary becomes a row with consistent columns. In this example, we create a Polars data frame from a list of dictionaries, where each dictionary represents one record. The keys in each dictionary become the column names, and the values become the data in each row. This method makes it straightforward to turn structured data into a data frame. Once created, the data frame is ready for further data manipulation and analysis. We print the data frame created from a list of dictionaries to see its structure and contents. This lets us check that the original list was correctly converted into a table. By inspecting the printed data frame, we can verify that the data appears as intended, and that the transformation accurately represents the desired data structure. We organize the data as a list of lists, where each inner list is a row containing a product name and the quantity sold. This structure keeps the order of information consistent across all rows, which is important for later steps, such as creating a data frame. For example, one row might record a sale of 3 books and another a sale of 10 pens. This row-based setup matches how the data naturally occurs and makes it easier to process and analyze. We create a Polars data frame from a list of lists, where each inner list is one row of data. The list is called Sales List Rows, and we define the column names using a schema with product and quantity as the headers. We set the orientation to row so Polars knows to treat each inner list as a separate row. This setup clearly defines the data structure and ensures each value in the inner lists is correctly mapped to its corresponding column. Now we display the data frame that was built from a list of lists to check that it looks correct. Viewing this output lets us confirm that the data has been properly arranged into the expected columns and rows. This step helps verify that the data frame structure and content match what we intended when we created it. This script shows how to create data frames in Polars from different types of input data. It first builds a data frame from a dictionary, where the keys become column names like product and quantity. Then it creates another data frame from a list of dictionaries, where each dictionary represents a sales record with the same columns. Finally, it constructs a data frame from a list of lists, this time providing the column names separately. All three methods produce similar data frame structures, demonstrating that Polars can flexibly handle multiple input formats. Loading CSV and Parquet. When you move from small, in-memory examples to real analytics work, you usually load data from external files, most often in CSV or Parquet format. CSV is a simple text format, commonly used to export data, while Parquet is a modern column-based format well-suited to large-scale data platforms. Polars is designed to read both formats efficiently, creating data frames with strong performance and good memory use. The main goal is to build a Polars data frame that faithfully represents your data, whether it comes from a small CSV file or a large Parquet dataset, so it is ready for further analysis. When loading CSV files into Polars, you need to think about how headers, missing values, and data types are handled. Polars can infer these automatically, but you can also set options, such as whether the first row contains column names or which delimiter to use. This is especially important for fields like dates or product codes with leading zeros, which might otherwise be misread as plain numbers. By configuring these details correctly at import time, you ensure your data frame is accurate and ready for reliable analysis and joins. Parquet files store built-in type information and use a column-based layout, which Polars leverages for high performance. In modern data platforms, where data is often split by date or region, Polars can read only the columns and partitions you need and skip the rest, making it efficient for very large datasets. This lets data scientists work responsively with big collections of clickstream data or shipment records. In practice, you will often mix CSV and Parquet files, and Polars offers a consistent way to load them into data frames for scalable analysis. Python code, loading CSV and Parquet. In this lesson, you will see how to load data into Polars DataFrames from both CSV and Parquet files. You will learn basic options for handling headers and controlling how data types are inferred when working with CSV files. Finally, you will compare loading the same dataset from CSV and from Parquet to understand how to do this efficiently and see the practical differences between the two formats. The line starting with an exclamation mark is a command used in environments like Jupyter Notebooks to install the Polars and PyArrow libraries before running the script. Polars provides efficient tools for data manipulation, while PyArrow is needed to work with Parquet files, a column-based storage format. Installing these libraries is an essential setup step so that the later data loading and processing code in the script can run correctly. We begin by importing several libraries that prepare our environment for efficient data work. Polars is used for fast data frame operations, similar to pandas but optimized for performance. Pandas helps us create and manipulate our initial data. PyArrow provides tools for working with columnar data, and its Parquet module lets us read and write Parquet files. Together, these imports allow us to handle data in both CSV and Parquet formats, using the strengths of each library. We begin by building a simple dictionary that stores sales records, with one entry listing order numbers and another listing the corresponding sales amounts in US dollars. This dictionary is then used to create a pandas data frame, which arranges the information into a table with columns for order identifiers and amounts. Organizing the data in this tabular form makes it much easier to work with, analyze, and manipulate in later steps. We start by choosing a file name for the CSV file, then use the pandas DataFrame export function to save the data to that file. We turn off the option that would include row index numbers, so they are not written into the CSV. This creates a clean CSV version of the data that can later be loaded into a Polars DataFrame. With this in place, we can compare how different file formats behave when used with Polars. To save data from a pandas DataFrame as a Parquet file, you first choose a file name and path for the output. You then convert the data frame into an arrow table using the appropriate function from the PyArrow library, because arrow tables are designed for efficient columnar storage. Finally, you use the Parquet writing function in PyArrow to write this arrow table to a Parquet file, creating a compact and fast format that works well for large datasets. We load data from a CSV file into a Polars data frame using a function that reads the file from the given path. We indicate that the file has a header row, so Polars can use the first row as column names and correctly understand the data structure. After the data is loaded, we print a confirmation message and then display the data frame to verify that the CSV content was read correctly. We begin by loading a Parquet file into a Polars data frame using the libraries function designed for this format, which is efficient for compact storage and fast access. Once the data is loaded, we display the data frame in the console. This quick check helps confirm that the data was read correctly and that its contents match what we expect. This script shows how to load data from CSV and Parquet files into Polars DataFrames. It first creates a simple sales record using a pandas data frame, then saves that data as both CSV and Parquet files. The code then reads each file into Polars, correctly interpreting the headers in the CSV and efficiently loading the Parquet data. By displaying both resulting data frames, it lets you compare how the two formats perform in terms of loading speed and data handling. Migrating from pandas. 2. When you switch to a new library for working with tabular data, you can make the transition smoother by keeping your existing workflow. Start by creating data frames from the same sources you already use, such as daily sales reports, but now with the new libraries tools. This helps you confirm that the structure and values match what you expect. Once you are confident in these basic results, you can gradually explore more advanced features like lazy evaluation or streaming reads. To migrate a data workflow, first identify the point where your data is initially turned into tables and replace that step with creating new data frames. Focus on loading data from common file formats, such as comma-separated text or Parquet files, using the same source your existing workflow relies on. Make sure the new data frame matches the original by checking row counts, column names, data types, and a few sample values. Once you have confirmed they align, update your transformations so they operate on the new data frame instead of the old one. Once you are comfortable working with data frames in the new environment, you can speed up your workflow by using lazy execution and efficient file handling. Instead of loading large datasets into memory right away, you define a lazy query that describes the operations and let the engine decide when and how to run them. This is especially helpful with massive datasets, such as in finance or web analytics, where you need to test scenarios often. For instance, a risk analyst can read only the required data, filter by time, and aggregate results without creating many intermediate tables. Over time, using lazy representations maintains compatibility with earlier practices while improving speed, scalability, and ease of maintenance as data grows. Python code, migrating from pandas. This lesson shows how to move from a pandas data frame to a Polars data frame and a Polars LazyFrame with a simple, direct migration. You will compare basic properties, such as the number of rows and columns, to confirm that the pandas and Polars data frames contain the same data. The goal is to let you begin with familiar pandas-style workflows while gradually adopting Polars-specific loading and usage patterns. By the end, you should feel comfortable transitioning your existing pandas data into Polars and verifying that everything matches. Before running the script, you may need to install the Polars and pandas libraries, especially if you are not working in an environment like Colab where they might already be available. This installation is usually done in a terminal or command line using a pip command that quietly installs both libraries without extra output. Completing this setup step is essential because the rest of the script relies on Polars and pandas for data manipulation and for comparing how data frames work in each library. We start by importing the pandas library, which lets us work with data frames for handling structured data in Python. We also import the Polars library, another data frame tool designed for higher performance, especially with large datasets. Using both libraries in the same environment allows us to create data frames in each, compare their behavior, and smoothly transition from pandas to Polars when needed. We begin by building a small pandas data frame that represents a simple daily sales report. It has 3 columns: day, region, and sales in dollars. The days are Monday, Tuesday, and Wednesday. The regions are East, West, and East. And the corresponding sales amounts are $120, $150.5, and $99. This basic structure mirrors a typical sales report and prepares us to later recreate the same data using Polars. This line converts a pandas data frame into a Polars data frame using the Polars constructor designed for pandas data. It is especially helpful for users moving from pandas to Polars because it lets them keep their familiar data structures while switching to a faster library. After conversion, the data can be processed using Polars' more efficient operations, providing performance benefits without changing the original dataset's layout. In this example, we create a Polars data frame directly from a dictionary, similar to how you might do it in pandas. The dictionary defines 3 columns called day, region, and sales dollars, each with its own list of values. This approach lets you quickly set up a data frame with predefined data. It also makes it easy to compare the Polars version with the pandas version and keep a consistent data structure across both libraries. A Polars LazyFrame is created from an existing Polars data frame to handle larger datasets more efficiently. It uses lazy execution, which means operations are not run immediately, but are delayed until the results are actually needed. This delay allows Polars to plan and optimize queries before running them. As a result, you can chain many complex data transformations together and still get better performance, especially when working with big data. We begin by printing the shape of the pandas data frame to see how many rows and columns it has, which quickly tells us the size of the dataset. Then, we print the shape of the Polars data frame that was created from the pandas one. By comparing these two shapes, we can check that both data frames have the same dimensions. This confirms that the data structure was preserved correctly during the conversion. We first list the column names from the pandas data frame so we can clearly see its schema. Then we list the column names from the Polars data frame using its columns attribute. Comparing these two sets of names lets us check that both data frames use the same columns. This confirms that the schema is aligned between the pandas and Polars versions of the data. This code works with a Polars LazyFrame, which delays executing operations, so it can handle large datasets more efficiently. It first requests only the first two rows of the data, then uses a collect operation to actually run the deferred steps and convert the result into a regular Polars data frame. Finally, it prints this small preview, labeled as lazy head, which serves a similar purpose to using the head function in pandas to quickly inspect the data. This script shows how to move from using pandas to using Polars for working with data frames. It begins with a simple sales report in a pandas data frame, then converts it into a Polars data frame, and also loads the same data directly into Polars as an alternative. The script creates a Polars LazyFrame to demonstrate lazy execution, which is helpful for larger datasets. It then compares the shapes and column names of the pandas and Polars data frames to confirm a match, and finally collects and prints the first two rows from the LazyFrame, similar to using the head function in pandas. Overall, it illustrates how familiar pandas workflows can be gradually adapted to Polars features. LazyFrame Schema Essentials: Building LazyFrames from Scans. When working with large or frequently updated datasets, it is more efficient to create a lazy data representation directly from the source instead of loading all the data into memory at once. With Polars, you can scan an external file or directory so it infers the schema, meaning the column names and data types, without immediately processing every row. For example, a retail analytics team might scan sales data and let Polars detect transaction, timestamp, and revenue columns. The key step is to confirm that this inferred schema matches what you expect from previous tools before proceeding to any calculations or visualizations. When you create lazy data structures from scans, the schema is inferred from metadata and a small sample of the data, which is efficient but can cause subtle mismatches with schemas from other systems. For instance, numeric columns with missing values may be treated as more flexible types, and date columns may be interpreted as text. To avoid problems, especially when migrating workflows like financial reporting pipelines, you should always review the inferred schema right after scanning. Confirm that column names and types match your existing reports, so the integrity of your analyses is preserved and you do not encounter unexpected behavior later. When working with lazy schemas, treat them as key objects to review before doing complex transformations. Right after scanning the data, check that column names match your existing dashboards and that each column has the correct data type, such as using categorical codes instead of generic integers. This is also the time to ensure sensitive fields, like birth dates, have the right level of precision. Carefully aligning the schema early helps the new pipeline fit smoothly into your existing system and reduces discrepancies in downstream comparisons. Python code, building LazyFrames from scans. In this section, you will see how to build lazy data frames using scan operations while inspecting and understanding their schemas. You will learn how Polars automatically infers column names and data types from external files, and how to review this inferred structure. Finally, you will adjust the schema so it aligns with expectations from earlier workflows that followed a pandas-style approach, ensuring consistency in column naming and data types. The line that begins with an exclamation mark is a command that installs the required Python libraries. It uses a package manager to add Polars for working with data frames, PyArrow for handling arrow data formats, and fsspec for managing file systems. Installing these libraries is necessary because the script will use them to read and manipulate CSV files with Polars. Without this setup, the later data processing steps in the script would not work. We begin by importing Polars, a library built for fast and efficient data manipulation with DataFrames, which we will use to perform our data operations. We also import the operating system module so we can interact with the file system. This allows us to create folders, organize files, and manage the storage needed for our data processing tasks. We begin by creating a directory called sales data to store our example CSV files. To do this, we use the make directories function from the operating system module. We set the option that allows the directory to be created without raising an error if it already exists. This ensures the script can run smoothly, even when the folder is already present. We create a text string that represents the contents of a small CSV file with 3 columns for transaction ID, date, and amount in US dollars. Each line after the header is 1 row of data, with values separated by commas. The example includes 3 transactions, each with a unique ID, a date in early January 2024, and a dollar amount. This simple dataset simulates daily sales with mixed data types and will later be written to a file for further processing. We create a new CSV file named Day1 in the sales data directory, making sure it uses UTF-8 encoding so the data is stored correctly. Into this file, we write structured CSV content that holds transaction details such as an identifier, the date, and the amount in US dollars. This gives us a simple, well-organized sample dataset that we can later use to demonstrate how lazy data processing works with the Polars library. We use Polars to build a lazy data structure that scans all CSV files in the sales data directory without loading them into memory right away. Instead, it creates a plan to read the files only when the data is actually needed. This lazy approach is efficient for large datasets and lets us inspect the data schema and apply transformations in advance. As a result, we can prepare and optimize our data processing without first loading the entire dataset. We begin by printing a short message to signal that we are about to inspect the schema inferred from the scan operation, which helps set the context for what comes next. Then we display the schema of the lazy frame, showing the column names and data types that Polars has automatically detected from the CSV files. This check is important because it lets us confirm that the structure of the data matches our expectations. Only after verifying this schema should we move on to applying any transformations. We rename the column in our LazyFrame from amount in dollars to revenue in dollars to match the expected naming conventions. This keeps our workflow consistent with earlier steps and with common pandas-based practices. Because the operation is lazy, the rename is only recorded as part of the plan and is not actually applied until the data is executed and processed. The code works on an existing LazyFrame that has already been renamed and changes the data type of the transaction ID column to a string using Polars. This ensures the transaction ID is treated as a proper identifier, which is commonly handled as text in data workflows. The change is defined lazily, meaning it does not run immediately but is added to an execution plan. This lazy approach allows Polars to optimize performance when the data is finally processed. We first print a short message to signal that we are about to display the adjusted schema, which helps keep the output clear when reviewing results. Then we access the schema of the processed data object, which reflects all the renaming and typecasting we have applied. By printing this schema, we can confirm that the column names and data types have been updated correctly and match what we need for the next steps in our data processing. To confirm that the lazy operations were applied correctly, we take a small sample of the data and inspect it. We first indicate that we are about to show sample rows after the lazy alignment. Then we limit the LazyFrame to the first 3 rows and collect the result, which triggers execution of the lazy operations. By printing this sample, we can visually check that the renaming and typecasting steps were carried out as intended. This script shows how to use Polars to build lazy data frames from CSV files and adjust their schema. It creates a small sales CSV file, then scans the directory lazily so Polars can automatically infer column names and data types. The inferred schema is printed, then updated by renaming the amount in dollars column to a revenue in dollars column and casting the transaction identifier column to a string type. The script prints the new schema and collects a small sample of the data to confirm that these lazy operations were applied correctly. Overall, it illustrates how lazy evaluation in Polars lets you work efficiently with large datasets without loading everything into memory at once. Deferred execution basics. Deferred execution is central to working with lazy data structures because it lets you design transformations without processing the data right away. When you build a lazy query, you are creating a blueprint that predicts what columns and data types will exist once the query runs. For example, with multiple CSV files of web analytics logs, you can define a lazy pipeline that selects, renames, and converts columns in a way that matches your usual pandas style. During this stage, no data is actually loaded, but the schema preview shows you the expected column names and types so you can confirm they will fit your analysis or machine learning needs. With deferred execution, validating the schema becomes a proactive step instead of something you discover only after running your code. This is especially helpful when moving from pandas because you can build a lazy query that mirrors your old workflow and then confirm that date, categorical, and numeric fields are correctly recognized. This early schema check is crucial in areas like finance or healthcare, where type mismatches can lead to serious errors. By confirming the schema in advance, you avoid finding problems only after long computations or after sharing incorrect results. Polars uses deferred execution, meaning it plans the entire query before running it, so it can optimize the steps while preserving the final schema you expect. With a full view of all transformations, it can reorder operations, push filters closer to the data source, and remove unnecessary work without changing your intended column names or data types. For instance, even if you rename columns and then change their types, Polars keeps the final schema consistent while executing these steps efficiently. This lets you build a lazy pipeline similar to a pandas workflow, but with better performance and scalability, while maintaining a consistent schemas across tools. Python code, deferred execution basics. This segment focuses on demonstrating lazy, deferred execution in Polars using LazyFrames schemas. It shows how you can inspect and predict the schema of a lazy query before any data is actually loaded or processed. You then compare this early schema inspection with the final result, after the lazy query is executed and converted into a regular data frame. The goal is to highlight how Polars lets you understand the structure of your data pipeline in advance, while still delaying the real computation until execution time. To prepare the environment for this script, you first need to install the Polars and PyArrow libraries using a package manager. These tools provide support for lazy data frame operations and efficient data processing. They are essential for enabling deferred execution and for inspecting data schemas as demonstrated in the code. Without these libraries, the script's core data handling features would not work. We begin by using the Polars library, which is built for fast and efficient work with data tables. Polars supports lazy evaluation, meaning it waits to run computations until we explicitly trigger them. This deferred execution helps avoid unnecessary work and can significantly improve performance. It also reduces memory usage by only computing what is actually needed. We begin by creating a small in-memory dataset that mimics simple web log entries. Each entry is a dictionary containing a user ID along with the number of clicks and miles. All three values are stored as strings, even though clicks and miles represent numbers. This basic structure gives us a simple dataset that we can later manipulate and analyze using Polars. We begin by creating a lazy frame with the Polars library from our in-memory dataset, which acts like scanning data from a source. A lazy frame lets us define data transformations without running them right away. This deferred execution means we can plan and combine operations first, then execute them later in an optimized way. As a result, we can improve performance by only processing the data when all transformations are defined. We build a lazy transformation pipeline on the lazy frame by first renaming the miles column to distance miles to make its meaning clearer. Then we use a column operation to convert the clicks column to an integer type so that numeric operations on it are handled correctly. Next, we convert the distance miles column to a floating point type to support more precise distance calculations. All of these steps are defined lazily, meaning they are only executed when the pipeline is explicitly run, which helps keep data processing efficient. We begin by checking the schema of our lazy transformation pipeline before any data is processed. To do this, we print a message that we are inspecting the lazy schema prediction, then access the schema attribute of the transformed lazy frame. This shows us the expected data structure and types that will result when the pipeline runs. By previewing the schema in this way, we can verify our transformations without actually executing the pipeline or loading data into memory. To turn a lazy pipeline into an actual data frame, you call the collect method on the transformed lazy structure. This call triggers all the deferred operations, so every transformation you defined earlier is executed at this point. The outcome is a concrete data frame that represents the final result after all lazy computations have been applied. After running the lazy pipeline, we now inspect the final data frame and its schema. We first announce that we are about to show the executed data frame and its structure. Then, we display the data frame itself, which contains the actual data after all transformations have been applied. Finally, we print the schema, which shows the concrete data types and layout of the data frame, confirming that every lazy operation has now been fully executed and materialized. This script uses the Polars library to demonstrate lazy evaluation on a small weblog dataset. It builds a lazy data frame, then applies a transformation pipeline that renames columns and changes their data types without immediately running the operations. The script first prints the predicted schema to show that Polars can infer the structure of the data before actually processing it. Only when the lazy operations are executed is the data materialized into a concrete data frame, and then both the final data and its schema are displayed. This illustrates how lazy evaluation lets you inspect and plan work efficiently without loading or transforming data until it is truly needed. Data frame, lazy frame, conversion. When you already have a complete data frame in memory, turning it into a lazy frame lets you use deferred execution while keeping the same schema. This conversion simply wraps the existing columns, names, and data types in a lazy query plan, without copying data or recomputing results right away. The original schema becomes the starting point for the lazy frame, so you can safely inspect or refine it. This makes it a convenient first step for working with schemas without changing any underlying data files or systems. When you convert a data frame into a lazy frame, you gain a flexible way to adjust the schema to match earlier workflows. You can standardize column names and refine data types, such as turning generic product code objects into more specific types or converting string dates into proper date and time types. These changes, including making categories truly categorical, are recorded as part of the lazy query plan. Because the lazy frame does not execute immediately, you can refine and review all these adjustments without triggering heavy computation or data movement too early. Converting an in-memory data frame to a lazy frame is useful for cleaning up and standardizing schemas in complex analytics pipelines that started in Pandas. For example, a marketing team with multiple campaign and customer data frames may have inconsistent data types or column formats. By using lazy frames, they can define a consistent schema that matches their reporting needs and apply lazy transformations to fix data types and align column names. All schema corrections are then applied together, producing reliable outputs that are ready for advanced analysis and avoiding scattered ad hoc fixes. Python code, DataFrame, LazyFrame conversion. This section explains how to safely convert a Polars DataFrame into a LazyFrame while keeping the schema consistent. It shows that when you apply lazy transformations, the structure and data types of the columns remain stable unless you explicitly change them. You then compare the schemas of the original DataFrame and the resulting LazyFrame before and after making changes, confirming that any differences are intentional and controlled. Before you can use the Polars library in Python, you must first install it with the pip package manager. Running the appropriate pip install command adds Polars to your Python environment. Once installed, you can then work with its DataFrame and LazyFrame features as used in the rest of the script. We begin by importing the Polars library, which is built for working efficiently with DataFrames and LazyFrames. It offers powerful tools for creating, transforming, and manipulating data structures, similar to what Pandas provides. However, Polars is optimized for performance and supports lazy evaluation, making it well-suited for complex data operations. Bringing this library into our script is essential because we will rely on its features for the data processing tasks we plan to perform. We begin by creating a dictionary that stores example customer data with 3 fields: customer ID, sign-up date, and revenue in US dollars. Each field is linked to a list of values where customer ID holds unique integer identifiers, sign-up date holds date strings from the year 2024, and revenue holds dollar amounts as formatted strings. This structured dictionary will then be used to build a Polars DataFrame so we can efficiently manipulate and analyze the data. We begin by turning the raw data stored in a dictionary into a Polars DataFrame. The dictionary holds customer IDs, sign-up dates, and revenue in dollars, and converting it to a data frame organizes this information into a structured tabular format. Once it is in a data frame, we can use Polars to efficiently manipulate, process, and analyze the customer data. We begin by printing the schema of the original data frame to see the data type of each column. This is important because it reveals the current structure of the dataset and how each field is stored. With this information, we can apply later transformations while preserving the correct data types and monitoring how the structure changes over time. In short, inspecting the schema first helps maintain data integrity throughout the analysis. We convert the existing Polars data frame into a LazyFrame so we can define operations without running them right away. This delayed execution makes data processing more efficient because multiple steps can be optimized together before they are executed. The LazyFrame keeps the same schema as the original data frame, so the data structure stays consistent while we prepare for later optimizations or transformations. Next, we print the schema of the LazyFrame to confirm that it matches the schema of the original data frame. This step checks that the conversion process has not changed the structure or data types of any columns. Verifying this consistency is important before applying any further transformations, because it ensures we are still working with the expected data layout. We plan changes to the LazyFrame without running them right away. We clean the revenue column by removing dollar signs and converting the values to a floating point number type, using a non-strict conversion to safely handle problematic entries. We also convert the sign-up date column from text to date objects, again in a non-strict way to avoid errors. Finally, we rename the revenue column to revenue dollars, and all of these steps are applied lazily, only when the data is actually needed. We now print the schema of the LazyFrame after applying our lazy refinements so we can confirm that all plan transformations are correctly defined. This includes checking that column types have been updated, columns have been renamed as intended, revenue has been converted to a floating point type, and dates have been properly parsed. By inspecting the schema at this stage, we verify that these changes are present in the LazyFrame before any actual data processing or execution takes place. To run the lazy plan and get the final results, you call the collect method on the refined LazyFrame. This action evaluates all the transformations that were defined earlier and turns the LazyFrame back into a regular data frame. Doing this is essential because it lets you see the actual data with every lazy transformation applied. As a result, both the schema and the values now match the intended changes. Finally, we print the completed data frame to check both its structure and its contents after running all the lazy operations. This step verifies that every planned transformation has been applied as intended. By viewing the printed result, we turn our lazy computations into a concrete output that we can inspect and validate. This script shows how to convert a Polars data frame into a LazyFrame while keeping the schema consistent and tracking how it changes with transformations. It starts with a data frame built from customer IDs, sign-up dates, and revenue values, then prints its schema. The data frame is converted to a LazyFrame, and the schema is checked again to confirm it matches. The script then defines lazy transformations that clean the revenue values by removing $signs and converting them to floats. Parse the sign-up dates into date objects and rename the revenue column, and it prints the updated schema to reflect these changes. Finally, it executes the lazy operations and prints the resulting data frame, showing the transformed data and the new schema. Schema alignment basics. Column types overview. When you switch between data libraries, it is important to understand how each one represents column types such as integers and text. Different libraries use different type systems, so reading the same file can produce similar but not identical column types. For example, one library may use a general integer type while another uses specific integer sizes, or may treat text as flexible objects instead of dedicated strings. Being aware of these differences helps you decide when you can reuse your existing data loading code and when you need to adjust the schema. Column types can be grouped into broad families and compared across libraries to see how they match. Numeric types, such as integers and floats, support tasks like financial modeling and scientific computing, while text types store things like product names and feedback, and may behave differently depending on how they are optimized. Temporal types, including dates and timestamps, are crucial for time-based analysis in fields like web analytics and healthcare. Logical types capture true or false values, and categorical types represent limited sets such as country codes. By mapping these families across libraries, you can see where they align and where differences might affect operations like joins or filtering. When reusing workflows across different environments, it is important to understand how each tool treats column data types. A pipeline might expect customer IDs as text and order dates as time zone-aware timestamps, but another system could interpret them differently, which can cause failures. This is especially critical for machine learning models that depend on correct recognition of categorical columns. By keeping a clear mental model of how each library handles data types, you can align your processes and make the adjustments needed to keep everything working properly. Column casting and renaming. When moving between different DataFrame libraries, it is important to adjust column names and data types so they match what existing workflows expect. Downstream processes may rely on a specific column name and type, such as a customer identifier stored as text, even if it looks like a number. Another library might load the same column as an integer or give it a different name. By carefully casting types and renaming columns, you keep schemas consistent and ensure your data frames fit smoothly into current pipelines without causing mismatches. Casting means changing a column's data type so it behaves correctly in calculations and matches what your team expects. This is especially important with data from CSVs or spreadsheets, where everything may be read as text or identifiers may be treated as numbers. For example, product codes with leading zeros need to be stored as strings so their format is preserved for accurate joins and merges. Likewise, converting date-like strings into proper date types ensures consistent time-based operations across different tools and libraries. Renaming columns works together with casting to keep your data labels consistent with what other tools and teams expect. Many organizations treat column names as informal contracts, so changing a name like net revenue can break dashboards, scripts, or reports. Different tools may automatically alter these names, so explicitly renaming columns lets you preserve the original naming scheme. This is especially important when adopting a new DataFrame library, because it allows you to explore new features while keeping existing interfaces and integrations stable. Python code, column casting, and renaming. This lesson focuses on basic column handling when working with both pandas and Polars DataFrames. You will see how to cast columns from one data type to another, especially when moving data between the two libraries. It also shows how to safely convert identifier columns into string types so they are treated consistently. Finally, you learn how to rename columns so they match the expectations of an existing data pipeline. After installing and using the pandas and Polars libraries, we begin by importing the pandas library and the Polars library so we can work with both types of data frames. Pandas is used for familiar, traditional data frame operations, while Polars is designed for faster and more efficient data handling, especially with large datasets or when performance matters. Setting up both libraries prepares our environment to perform data transformations and to convert data back and forth between pandas and Polars data frames. We begin by setting up a pandas data structure with two main columns. One column stores numeric customer identifiers, and the other stores revenue values as decimal numbers. This kind of layout with identifiers alongside numerical data, is common in data analysis. It prepares the dataset so we can easily perform calculations and other operations on these values later in the process. The code first announces that it will show the original pandas data frame and the data types of its columns, setting the context for the output. It then displays the data frame in a table-like form so you can see the current values. Finally, it prints the data type for each column, which is essential for understanding the structure of the data and planning any operations that depend on those types. We begin by converting a pandas data frame into a Polars data frame so we can move data between the two libraries. Using the Polars function that imports from pandas, we take the existing pandas data and transform it into the Polars format. Once the data is in Polars, we can use its features for tasks like changing data types and renaming columns. These operations are useful when adapting the data to different processing pipelines or analysis workflows. We start by showing the initial state of the Polars data frame to establish a baseline view of the data before making any changes. First, we print the full data frame so we can see all the values it currently contains. Then, we print the schema, which lists the columns and their data types. This information is essential for understanding how the data is structured and for deciding what transformations may be needed next. We modify the Polars data frame by changing the data type of the customer identifier column. Using the method that updates columns, we select this column and cast it to a UTF-8 string type. This ensures the identifier is treated as text rather than a numeric value, which better reflects its meaning. We then keep the original column name using an alias so the overall structure of the data frame remains consistent. In this step, we rename columns in a Polars data frame so they match a different schema expected by existing data pipelines. We use the rename method to change the column names. For example, the column called customer_ID is changed to customer ID, and net_revenue is changed to net revenue. This ensures the data frame follows the naming conventions required by downstream processes or systems. We now display the final Polars data frame to show the result of our casting and renaming operations. First, we print a short message indicating that this is the final version. Then we print the data frame itself, which now includes the updated column types and names. Finally, we print its schema to confirm that all data types and column names reflect the transformations we applied. This script shows how to convert a pandas data frame into a Polars data frame while adjusting column types and names. It starts with numeric customer identifiers and revenue data in pandas, then converts the data to Polars and inspects the schema. The customer identifier column is cast to a string type to better reflect its role as an identifier rather than a number. Finally, the columns are renamed to match a different naming convention. And the updated Polars data frame and its schema confirm that the casting and renaming were successful. Aligning schemas with pandas' expectations. When moving data between tools, you need to make sure the structure of your data frame matches what your analysis expects. This means checking that column names and data types are consistent with those used in earlier work. If a team expects a column to be a string, but it is treated as an integer, or if names differ, the analysis can fail. Aligning schemas is the process of reviewing and adjusting these details so your data remains compatible with existing workflows. When aligning schemas, focus on preserving the workflows your models already rely on. In a recurring financial report, for example, the model may expect specific column names and data types, such as a date field stored as a calendar date and a revenue field stored as a precise number. Small changes, like renaming or capitalizing a column or switching a number type, may not break the system outright, but can quietly distort results. In healthcare data, even changing patient IDs from text to numbers can break joins without obvious errors. Keeping schemas consistent with established expectations reduces these hidden risks and helps ensure reliable, comparable outputs across tools. In collaborative and regulated settings, keeping data schemas aligned is essential for reproducibility, auditability, and trust. When sharing data, especially in areas like public policy, insurance, or pharmaceuticals, partners depend on agreed schema documentation. So any internal changes to column names or types must be adjusted back to the documented standard. Strict adherence to these schemas is often required for regulatory submissions. Treating schema alignment as a core step in data preparation helps ensure consistent, reliable data across different tools and environments. Python code. Aligning schemas with pandas' expectations. This section focuses on making a Polars data frame compatible with an existing pandas-based workflow. It shows how two similar data frames can still differ in column types or names, which can cause problems when you try to use them interchangeably. You will learn how to identify these mismatches between the Polars and pandas versions, and then adjust the Polars schema so that its column names and data types match the trusted pandas schema. By the end, Polars will align with the expectations already established in your pandas pipeline. The comment about installing Polars and pandas is simply a reminder to make sure these libraries are installed in your environment. It is not meant to be run as code, but to prompt you to use a package manager if needed. This step is important because the script depends on both libraries for data manipulation and aligning data schemas. We begin by importing the pandas library for data manipulation and analysis in Python, and the Polars library, which provides a fast data frame implementation optimized for performance with large datasets. Using both libraries in the same environment lets us work with pandas and Polars data frames side by side. This setup allows us to focus on how to align their schemas so that data is structured consistently across both tools for reliable and comparable processing. We begin by defining a pandas data frame that represents the structure we expect our data to follow. It has one column for campaign identifiers, such as A101 and B202, stored as text, and another column for revenue values, stored as integers in cents. This data frame serves as the trusted schema that later data should match. We begin by creating a Polars data frame from a dictionary, where each key becomes a column name and each list provides the data for that column. One column is called campaign ID and holds integer values, and another is called revenue dollars and holds floating point values. These column names and data types are chosen to be different from those in a pandas data frame, so we can later demonstrate how to align the schemas between the two frameworks. We start by printing a short message to let the listener know that we are about to show the schema and data from a pandas data frame. Then, we use a pandas feature that lists the data type of each column so we can understand the structure and kinds of values in the dataset. Finally, we display the first few rows of the data frame, which gives a quick view of the actual data and makes it easier to compare this data frame with other data structures later. We start by showing the original schema and data from the Polars data frame so we understand its structure before making any changes. A short label is printed to indicate that we are viewing the Polars schema and data. Then we display the schema, which lists the current column names and data types. Finally, we show the first few rows of the data frame to provide a quick snapshot of the actual values it contains, which we can later compare with the pandas data frame. To make a Polars data frame match a pandas data frame, we first rename the columns so that campaign ID becomes campaign ID and revenue dollars becomes revenue cents. We then adjust the data types to be consistent with pandas. The campaign ID column is converted to a string using the Polars text type, and the revenue cents column is created by multiplying the original dollar values by 100 and casting the result to a 64-bit integer. These steps ensure both the column names and data types line up, allowing the two data frames to integrate smoothly. We start by printing a short header to indicate that the following output shows the aligned Polars schema and data. Then, we display the schema of the aligned Polars data frame so we can see the structure and data types of each column after applying the necessary transformations to match pandas expectations. Finally, we print the first few rows of this data frame to visually confirm that the column names and data types now match the expected format. This script shows how to align a Polars data frame with the schema of a trusted pandas data frame. The original pandas data uses the column names campaign ID and revenue in cents, while the Polars data uses different names and stores revenue in dollars. The script first prints both schemas and data to reveal these differences, then renames the Polars columns to match the pandas names. It also converts the campaign identifier to a string and multiplies the revenue values by 100 so they become integer cents. Finally, it prints the updated Polars schema and data to confirm that they now match the pandas expectations. In this lecture, you learned to create Polars DataFrames and LazyFrames from in-memory data and external files that are commonly used with pandas. Inspect and adjust Polars schemas to ensure column names and data types match expectations from existing pandas workflows. And compare pandas and Polars data loading patterns to identify where direct one-to-one translations are possible. In the next lecture, Lecture B, we will go over selecting and filtering.
Thank you for your attention. See you all in the next lecture.